Today we're going to talk about the binomial distribution. So we're going to look at a particular model for a random variable. We look at general discrete random variables, and Bernoulli was kind of a special case. In this one, we are looking at, we have n cases, or sometimes these are called trials, or observations. We're going to assume that each is independent of the others. Different items you're inspecting, or you're going to different lakes and inspecting those, or you're randomly picking people and asking a question about that, or you're doing some process over and over again where it's independent of each other. Each trial is going to be a binary outcome on each one. Sometimes, this might be yes or no. Does the individual have a particular disease or not? Do they have a certain opinion or not? Is somebody female or male? Depending on what you're asking. Sometimes it's called success or failure. And so if you're asking, does somebody get better from medical treatment? Is it a success, or not getting better is medical? But sometimes you count the opposite. Success is not really a success. You're just kind of counting the number of times something happens. So you have a big group. What's the rate of some rare form of cancer? Well, having it is not really successful in that sense, but you're counting it. So success is really counting one outcome versus the opposite. So there's binary outcome on each one. The probability of yes or one particular outcome is the probability p between 0 and 1. And so the probability of the opposite outcome no is just 1 minus that. And the thing that we count is the number of times that we get a yes out of all of the subjects. So our random variable, maybe I'll write it on that. Right here it is. X records the number of yes outcomes out of the n trials. So it's going to be outcomes like 0 or 1 or 2 or up to n if it is our number of trials. So if we do a survey of 300 people, it's going to be some count of the number of people there. So today we want to think about the probability distribution for that. What are the probabilities of all the different possible outcomes? What's the average? What's the variance? And some application. And we'll do a little work to show that when we get probabilities, it actually is a probability distribution, and kind of look at how to get the mean and variance a couple ways. Okay. So let's start with an example though. So the CDC, Centers for Disease Control, puts out something called the Morbidity and Mortality Weekly Report. A weekly report that focuses on different health topics across the U.S. It can range from everything from infant death to things with Parkinson's disease and Alzheimer's to whatever. And it's been published for decades, and is a summary of different things. So the one that came out, what's the actual date, on the 1st, right, considers adolescents toothbrushing, children age 3 to 6. There's a concern that they're using too much toothpaste. Now, it's not, this is more information that maybe they're using too much toothpaste, right? And so the recommendation for small children is to use a small amount of toothpaste with fluoride, right? And you don't want to get that because it kind of crosses the brain-blood barrier and So children don't necessarily start brushing their teeth right when they're infants, but once they start coming out, very little. So the idea is to get a toothbrush, so just a little smear of toothpaste, almost nothing, like a little pea size or smaller. But many kids are taking a bunch and getting this like an adult would need to do. The consequence of this, I know it doesn't have to talk about very serious consequences, but some children get little lines in their teeth, extra white, and a few other things. So but they're just using more than they seem to need, right? So this breaks it down by a number of race ethnicity groups, by age groups, and gives the race. But it said there's a survey, a study of 5,057 children in all. And the rate at which they're using too much toothpaste in this age group is about 38%. Now, of course, this is something that's hard to communicate and get good results on it, because you say, oh, children shouldn't use so much toothpaste. You don't want them to stop using toothpaste and brushing their teeth and even flossing. My brother's a pediatric dentist, and some of his public health work has been going to places like Jamaica, or he's been in New York City going to underserved schools. And a lot of the kids just have horrible teeth by the time they're 6 or 7. If you don't brush your teeth, if the kids don't brush their teeth, and if the parents don't take care of them, and they put them to bed with juice or milk or something like that, their teeth can be rotten by the time they're 5 or 6. Right? So they have to take care of their teeth, but at the other time, they don't need to put a full adult-size toothbrush with a full adult-size glob of toothpaste with fluoride in there. They don't need whiteners, they don't need extra abrasive stuff, and they don't bleach, they don't need to bleach their teeth at that age. So there's things that they don't need to do. So let's say instead of having all these children, we have 5 children. So what's the chance that we have 5 children and none of them use too much toothpaste? These 5. These are not, we're going to assume that these children are independent, right? How would 5 children that we might select not be independent of one another? Yeah.
They're in the same household.
The same household, the parents are doing the same thing to all the kids, right? So these would be maybe 5 children in unrelated households. So none use too much toothpaste. If X is the symbol for the number who use too much, that's the probability that X equals 0 in this case. Right? What do you think the probability, how would we calculate that probability? What's the chance that the first child does not use too much toothpaste? Yeah.
We need to find out the number of children that do use too much toothpaste.
Well, we can, yeah, so the thinking is that maybe we would do how many don't use too much toothpaste. So we can look at maybe 2 extremes, right? Let's say the more extreme is that all the children use too much toothpaste. We could also have numbers that are in between 1, 2, 3, 4, and so on. The chance that they all use too much would be that this binomial random variable has a value of 5. Right? What's the chance that all the children use too much toothpaste if they're independent? And the probability for each one, if they're randomly picked from this population. And we have 38% of the children nationwide in a certain age group use too much. What would be the probability that the first child uses too much?
38%.
38%. And the second child, 38%. Right? So there's going to be 0.38, and there's 5 children that use that too much. And so that's about 0.8% at the time we get 5 children. How about the other extreme, that no children use too much toothpaste? Yeah.
Would it be sorry, math would be 0.62 to the fifth.
Yeah, that's 0.62 to the fifth, right? And that one is 0.092. That's a little more common. You have 9% of your sample of 5 don't have it. Right? Now the other ones, X could be, 1, 2, 3, or 4. So let's talk about calculating those probabilities. So we have 1 child out of the 5, 2 out of 5, 3 out of 5, or so on. What's the chance that 4 children use too much? Like out of 5. Let's imagine one particular sequence of children, right? That we have 5 children here. 1, 2, 3, 4, 5. And if 4 of the children use too much, right? We'll say maybe yes, put a Y here for yes. You could have the first 4 children use too much, right? And the 5th one's okay. They're using just a little tiny bit, right? Or not, they're not using too much. That'd be one way that could happen. Or you could have, the 4th child be the one out of those 5, right, that uses the right amount, but or not too much. So how many ways is it possible to get a selection of children such that you just get 1 that's no and 4 that are yes?
5 choose 1.
So 5 choose 1. That's equivalent to 5 choose 4. Right? Either choosing the yeses or choosing the no's. What's the probability of one particular sequence? Just to remind you that the probability of a yes was 0.38, and the probability of a no was 1 minus that, 0.62. What's the probability of that particular sequence, the first sequence there of children? The probability of this sequence. So 0.38 for the first child, 0.38 for the next one, and so on. And then 0.62. So it's 0.38 to some power times 0.62 to times some power. And if it's 4 yes, then it's 4 here, and then it's 1 over here. Do you believe that it's the same probability for all 5 of those sequences? So that could happen 5 ways. So since we're counting the 4, and put 5 choose 4 there, it's going to be the same numbers. It'll be 5 times the 0.38, 4 times 0.62, and that number is 0.065. A little bit more likely than having 5, which was more extreme, right? But that's the probability. How about the probability that we get 3 children who use too much toothpaste? What's the analogy to that type of reasoning? How would the formula change?
We would change what we're choosing, so it would be 5 choose 3, and we'd have to change the powers because we're now looking for 3 yeses and 2 nos.
Yep. Yep. 0.38, 38 cubed, and 0.62 squared. So one typical sequence could be yes, 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 no, no. 3 children use too much, but 2 don't. Right, so we end up with this. That's an 8 in there. 5 choose 3. What's 5 choose 3? It's the same as 5 choose 2. You can calculate it as 5 choose 4, 5 times 4 over 2 times 1. And so there's 10. There's 10 ways to put 2 no's on there and 3 yeses. If you calculate out the whole probability for 3, it's 0.212. And so the others continue like that. So the whole probability distribution is going to be listing the probabilities for 0, 1, 2, 3, 4, and 5 out of our 5 children. right? And if we do that calculation, so the values of x that we can have, 0, 1, 2, 3, 4, 5, probabilities that we get are 0.092, 0.281, 0.344, 0.212, 0.065, 0.008. And those would be the different probabilities for that distribution, right? You can make a graph of those. You know, 1, 2, and 3 are the most common, but you know, 0's going to happen if you take a group of 5 children, say 5 children per day, right? Or 4 is going to happen. If you take enough groups of 5, you're probably going to get 5 sometime, but less than, it's going to be a little bit more unusual, right? If you got a series of 5s, you know, different groups of 5 children, and then all of these children are using way too much space, right? I don't know. You might wonder if this is a special group that's much different than the 38% for each one, right? So, but what's the general formula? Right? So we have n cases or trials or subjects, children, and k is the number of yes responses, and p is the probability of this yes for one case. The possible values of k, we're counting the number of yeses. K can go 0, 1, 2, right up to n. We want to know if x is the number of yes, so number of yes as a random variable. This is, we have some values, k, that are actual numerical values. Right? So we want a formula that we want to think about. Can we get a general formula? What's the probability that we get k successes out of our n? Let me figure it out. So what do you think we need to do? Toggle back and forth a little bit. What's our formula going to have in it? We're going to have a probability, 1 minus a probability. How many times do we get yes? We're going to have some p and some 1 minus p in here. How many times for yes? Yeah, there's going to be an n choose k, right? There's some combinatoric out there. There's a k up here, right? We need k yeses. So how many no's? N minus k, right? And so this would be the probability of one particular sequence, say all yeses, k yeses, n minus k no's. Well, this is the number of ways of coming up with how many ways you can rearrange to still get that sequence, right? So these are our probabilities for k going from 0, 1, 2, right, up to n. And so those are the binomial probabilities. So if you're counting something and it has these characteristics, you have a fixed number of trials n, a probability p of success of yes on each one, and they're independent, you count the total, that's the probability distribution. The probabilities can be determined for all the different cases. Now let's look at 2 special cases. So when n was 5, what happens when k is 0? This says, you know, x is 0, so this formula is going to be n choose 0, right, p to the 0, right, 1 minus p to the n minus 0. And this n choose 0 is kind of a funny looking thing, but that's defined to be 1. Right? So if you have nobody who qualifies as that event, that can only happen one way. Right? Everybody is no, 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 no. Right? So there's only one of those. In the special cases, the 0 factorial is defined to be 1. You wouldn't necessarily think about that. 2 factorial is 2 times 1, and 1 factorial will be 1 times 1, but 0 factorial just gives us a special way to do 0 things is one thing. So if this is 1, p to the 0 is 1, and that's just 1 minus p to the n, like we did at the beginning. And the probability that x equals n also works out just to be, well, each one had to have a success to an n. N is 1. If there's only one way to choose everybody to have yes, you know, a string of yeses, there's only one way to do that. And then the 0 factorial would be in there still. So anyway, those two special cases work out. All right. 2 questions. Any questions about why this formula works? All right, so a different example. In pregnancies, the rate of multiple births, twins, triplets, and so on, the probability that a woman has a multiple birth is about 3.3%. And say during a week, a moderately sized hospital, maybe kind of a large one, has 50 pregnancies. What's the probability? And so X is going to be the number of multiple births that occur at this hospital. Multiple births are more risky, they often result in lower weight babies, they have other complications, so you need some special resources for handling that. So if you have 50 pregnancies come through in a different week in a fairly decent-sized hospital, what's the probability that you get less than 3, less than or equal to 3? So this would be multiple births. Less than or equal to 3 times for the 50 pregnancies. That there's 3 or fewer women who have multiple births. What's the chance that it's bigger than 3? We'll figure out that this first one, where the chance that it's bigger than 3, right, so you have 4, 5, 6, all the way up to 50. You're not really going to have 50 multiple births. It's really a random sample, because it's so rare. Right? Is 1 minus this. So we can think about computing this. Right? So does it fit this binomial model? 50 women, we're going to look at that number of pregnancies. If it was random, how many pregnancies you're going to look at, you're just going to look like a week, and maybe you're going to have 50, maybe you're going to have 60, 40. That would be kind of invalidated a little bit. Right? You don't know anything a priori about risk factors for the women. Have they had previous multiple births? Does it run in their family? Are they using in vitro fertilization or something like that? Are they older mothers? We don't know anything like that. We're just really willing to use the 3.3% in general. If these women are unrelated to one another, right? They're not sisters or something like that. Some studies might go on for a period of time to accumulate a number of, so it's possible if you're doing a large enough study that you get people related to one another if you're taking, in a particular town. So with this, it seems reasonably binomial. Right? To get less than or equal to 3, right? That's 0, 1, 2, or 3. So if we calculate the probability that we have those different outcomes and add them together, we'll get the probability less than or equal to 3. So what's the probability first that we get 3 pregnancies out of 50? What do I want to write down for the formula?
50 choose 3.
50 choose 3. Good.
Times the probability.
So the probability that I gave was 0.33. for a multiple birth.
Raise to the third.
You know, so 3 women have that outcome. So 1 minus the probability they don't. That's 9, 6, 7 in there. And so the remainder is 47. Yeah, 47 right there. I'm probably going to do this on a calculator. 50 choose 3 though. If you wanted to calculate it by hand, you can do the 50 times 49 times 48, 1 times 2 times 3, and get some number. I don't think I actually wrote down that number, but the final answer probability is about 0.145. Okay. So about 14.5% of the time, when you have a collection of 50 women, if they're independent of one another and the rate of preterm birth is 3.3%, right, then about 14.5% of the time you're going to show up with 3 women. Right? What the chance that is 2? Well, it's 50 choose 2. It's going to be a smaller number. 0.033 squared. The 0.967 squared, to 48, sorry. And that's 0.266. It has more decimal places, but this will be enough decimal places for now. And the probability that x equals 1. 50 choose 1 is just 50. 0.033 to the first. Then 0.967 to 49. That probability is 0.319. It's more likely that we'll get 1 out of that. The chance that you can get 0 is just basically 967 to the 50th, right? None of them have it, multiple births, and that probably is about 0.187. So the chance that you're 3 or less, right, you would add these 4 probabilities together, right? So the probability that x is less than or equal to 3, 0.187 plus 0.319 plus 0.266, and that one that's up here is 145. 5 and 0.917. So about 92% of the time, approximately, right, out of 50 women, there's going to be 3 or fewer that have multiple births. So is there a real chance that we're going to see more than 3 women? The opposite is about 8%. Right? So sometimes you will see, right? So if this is a weekly accumulation of women going through a hospital system maybe, right, then yeah, you're going to see more than 3, so some of them need more resources to be ready. Right? So 2 questions. One, is this a legitimate probability distribution? Basically, this means that if you do the sum, do probability sum to 1. So if you add all the probabilities for the different values, a range of 0 to n, the probability that it's k, particularly k, was in choose k, p to the k, 1 minus p to the n minus k, does that equal 1? Yes.
Are we asking this as a pregnancy example?
Just in general, any example. You have a fixed number of n, you have a binomial random variable, so this is the probability for k out of n. Does it work for any of them? The pregnancy one are the numbers that I wrote down. I didn't calculate all the way up to 50. you know, I just did 0, 1, 2, 3, but if I went all the way up to 50 and captured enough decimal places, it would be really close to 1 when I add them. It might be off by 0.0001, you know, by rounding, but kind of practical computation might be off slightly, but in theory, does it actually add up to 1, right? We had one result before that's kind of useful, right, to look at this. With probability and stories, we thought about how can we expand a term here, x plus y to the n, right? What's another way of writing that? And we argued that you could write this thing, well, you have a certain number of x's and a certain number of y's that are going to be in every term as you expand that. Right? Each time you're either going to get an x or you're going to get a y. Right? So if you get k x's, you get n minus k y in your terms as you multiply all those things out. Right? Every product, once you multiply out all those, is going to have n terms and multiply together, and they're going to split between x's and y's. Right? How many ways can you get k x's? That's our combinatorial, combination n choose k. Right? If you choose, there's n terms multiplied here. You choose k of them to contribute an x. Then n minus k of them contribute a y, and these things were the same, right? So these look similar. Right? Maybe we can choose values of x and y to match this problem. Right? So if we believe this is true, right, because of the story problem type of thing that we said, why would the other one be true? What values, how do you want to equate x and y to the binomial problem we're interested in?
X is p and y is 1 minus p.
Yeah, right. So if x is p, and y is 1 minus p, that's going to match this one, right? Now we just need to see, we have x plus y, is x plus y to the n with those choices equal to 1, right? So if x plus y to the n, and we put in p plus 1 minus p to the n, that's just 1 to the n because the p and minus p is 1, so just 1. So yeah, because of this general formula here works, in the special case where x and y are p and 1 minus p, some two probabilities, then they do add up to 1. That's good. I mean, we'd want that to happen, for it to be probability distribution. But with probability distributions, we also get characterized by mean and variance. What's the expected number of outcomes? In the pregnancy example, the expected number of mothers who have multiple births. So expected value. So what's the expected value of x? Here x is a binomial random variable. And for binomial, when I'm talking about it, I usually write the sample size and the probability. So those are the two things you need to know. You need to know that the problem follows a binomial experiment setup, right? So that it applies, and you need the sample size and the probability. Right? What was our definition of expectation? Right, so we took all our values times their probabilities, right? The values weighted by the probability. So in this case, our values go from 0 to n. Here's k is our value. N choose k. P to the k, 1 minus p to the n minus k is the probability. Right? So now we want to try to simplify this to get a nicer form. And one thing we can do when you encounter something like this is we have a symbol here that's a little more complex. So let's write out what that is. Right? N factorial, k factorial, k factorial, p to the k, 1 minus p to the n minus k. expand things out by how they're defined. What happens when k is 0 at the first term here? What happens to that? What value are you adding in for the case where k is 0?
0.
0, right? 0 factorial is 1, but k times that is 0, right? Whenever you had a random variable that's a 0, it doesn't add anything into the expectation. Right? It's still meaningful, because if you have a lot of probability at 0, then there's not much probability on the other things. So it matters for the expectation, but it's 0. So we can write the summation taking out the 0. So k n factorial, k factorial, n minus k factorial, p to the k, 1 minus p to the n minus k. What could you do now?
You could pull out the p to the k and then 1 minus p to the nk.
You can pull some things out. Well, so k is changing. So k, anything that has k directly in it can't be pulled out because its value depends on what the value of k actually is. So you could pull n factorial out because n factorial is just the biggest number. It's not changing with the sum. So you could pull that out. That's a good idea. Often you can pull things out that are constant. Let's do one other thing first. Is there anything you can cancel? So we have a k and a k factorial. Right? So what is k over k factorial? So that's k over k factorial is k times k minus 1 times k minus 2, all the way down to 1. Right? So if the k's cancel, we're left with k minus 1, k minus 2, all the way down. Right? And that can be written more succinctly, right, as k minus 1 factorial. So 1 over k minus 1 factorial. So, I'll do it on the next page. So if we canceled the k, so now k is level, we're going from 1 up to n. We have an n factorial, k minus 1 factorial, n minus k factorial. So p to the k, 1 minus p, n minus k. So we've done a little bit of work. Now we know that the binomial probabilities add up to 1. Right? So what we want to try to do is rearrange, because it's starting to look like a binomial probability. Right? There's something that kind of looks like a combination, but it's a little bit off. A p to a power, 1 minus p to the power. So it doesn't quite match up with n and k, like that. It's going to be a little bit different. But it's getting close. Right? So maybe we can change things so that we get a different binomial in there. One problem for doing a binomial probability is this doesn't start at 0. Right? Our sum of our binomial probabilities going from 0 to n or 0 to whatever the sample size is, right, for our application adds to 1. But this starts at 1. Right? So let's change it. So it starts at 0 again. We want something to start at 0. So k, maybe I'll call it L. We want L to go up to 0. So what's the relationship between L and k if I'm going to make a change here? It looks like I want to make it 1 lower. Right? So if I do k minus 1, then the lowest value of L is 0. I'm kind of looking at it the other way. K is L plus 1. That's the relationship between the indices. We're going to change the indices to try to make it look nice. So if L goes from 0, what should be the upper limit for L? What was the upper limit for k? N. N minus 1. So now let's replace k everywhere in here by its version of L. Right? So n factorial is still the same. K minus 1, that is L. Right? So L factorial. There's n minus k is L plus 1. So subtracting, there's an L minus 1 factorial. Right, so k was L plus 1, so if I'm subtracting it all, it can be written like that. P, now we replace this k, looks like L plus 1, goes here, and 1 minus p, and this is n minus L minus 1. Just put it there. So now at least we have it going from 0 to some number. But things don't quite match what we want. There's a little extra stuff in there, actually. What's one thing that looks extra? In general, when the index for probabilities went started at k, it was p to the k, 1 minus p to the n minus that thing, right? But now we have, looks like an extra p. What can we do with that extra p, right? P to the L plus 1 is p to the L times p. What can we do with that extra proportion there, that extra probability? Your initial suggestion is relevant.
Can you turn it into like the x plus y thing? That's what I was originally thinking.
Oh, we're thinking about
Yeah.
that, yeah. So that's also good to think about doing that. The reason this is a little bit different than the x plus y because we get this extra k stuck in there. Right? So something like that will be useful, but so trying to reuse that idea is, once you're doing different proofs and different derivations, it's good to think about what you've done in the past. So yeah, that's good. But anything that's constant, see, all this is one term here. And there's a value of that for L equals 0, L equal 1, L equal 2, all the way up to the top. L equals n minus 1. They all have an extra p in there, right? So if you have a bunch of terms, they all have p multiplied on there. You could pull p out. And so this p, that extra p, can be written on the outside. So you can write p to the L, and then 1 minus p, I'm going to reverse it, n minus 1 minus L. That's okay, right? And then over here in the denominator, we have L factorial, n minus, I'll write n minus 1 minus L factorial. And so that n factorial, well, with our binomials, usually when we add these things together, it gives our total sample size, right? But L plus n minus 1 minus L is n minus 1. Right? And in the numerator, we have n. So, but n factorial can be written as n times n minus 1 times n minus 2, going all the way down. So if you focus on grouping these together, that's n minus 1 factorial. We kind of have an extra n in the numerator. N's a constant number, that's 50, that's not changing with that summation, so it can be brought out. And what gets left in here is n minus 1 factorial. This extra p and this extra n apply to every single term, so you can factor it out of the sum. So, what is this summation then? I'm going to rewrite it a little bit. 0 to the n minus 1. There's a p to the L, a 1 minus p to the n minus 1 minus L. This part over here is really n minus 1 choose L. There's n minus 1 factorial over L minus 4 factorial, and then n minus 1 minus L factorial. So these are the probabilities for a binomial as if binomial, where if you had n minus 1 trials and a probability of p. Right? These would be the probabilities here. But what happens if you add all those probabilities from 0 up to the sample size? Right? That's our 1 again, right? Those probabilities add up to 1, so they go away, right? So our expectation is just n times p. So if we had 50, whatever the sample size is in for our application, whatever the proportion is, the expected number of cases that say yes or have that success, some indication of that group, which is the number of trials times the probability for each one. Is that kind of an intuitive result? Does that seem reasonable? Yeah.
Are we gonna ask to do that out on like a test?
Not probably the whole thing, right? So one way if I ask about some of these things is give kind of one equation and another one, and there's just a couple manipulations to move things around. Right? More likely it'll be on a homework on the next. Homework would have you do some manipulation, you know, or give you options of answering things in different ways, right? So like the story problems on the previous homework, right? You could do the algebra, you could write a story. Some people did numerical examples and got most of the credit, right? So, but it's but this is kind of the theory that's going on behind the probability. Actually, figure out, show that that's what this is. So some balance, right? Not a full blown thing as long as this. Right? But in this course, it's good to see some of these things. These things, if you would go on and take a more advanced course in probability or a more mathematical one, could do more manipulations like this, right? And, you know, or any scientist, any applied, you know, math program or thing that would have applied math dealing with equations and things, you might end up manipulating some summations to figure something out or solve for something. Right? And so some of these techniques of you know, we just wrote out the definition. We expanded some term that was defined. We, you know, think about, well, what can you do? Well, so at 0 that cancels, or maybe you cancel the k's. It turns out to be easier to deal with it if you do this step than that step. That's kind of, I just know that from experience. So, and then, you know, change of formulas was useful. So those steps could be used in other applications. They just all kind of come together here in this one. Most of the problems will be more applied, right? So in the example with 50 pregnancies, the probability that one woman has a multiple birth was 0.033. How many are expected? How many multiples are expected? So let's pick the value of the number. The formula is just n times p. So n in this, is it clear that what n and p are in this case? Right? So 50 women, 0.033. So that's 1.65. 1.65 multiple births on average. It's fine that it's an integer, you don't need to round it. Right? Imagine you could have 50 at this hospital system, 50 at this hospital system, 50 at this hospital system. And every time you count the number of births, you're going to get 0, 1, 2, 3, you're going to get an integer number. Right? And the average of those in the long run is going to be about 1.65. It's definitely, a lot of the probability was down there, 0, 1, 2, 3. Less probability at 4, 5, and above. Almost no probability at 50. That would be just bizarre to have all those in a row. Unless it was a specialty clinic or something. What happens if there's 500 pregnancies? Say a smaller hospital, maybe 500 women per year coming through on maternity ward. Right? How many multiple births do they expect during a year? Again, if it's all binomial, it'd be n times p, so 500 times the 0.033, and so 16.5 multiple births expected. So if you track this over the years, and you saw a great decrease or a great increase beyond that, you might wonder what's going on in the county. Standard deviation. But any questions about applying that? We also can look at the variance of a binomial random variable. So we can, now the variance of a random variable is the expectation of that variable minus its mean, which is NP in this case, squared. But you can figure it out by taking the expectation of x squared minus the mean quantity squared. Right? Those two formulas give you the same thing, right? You get we went through how to get this equivalency, right? You square that thing out and then take the expectation across different things and it works out. So you could, we're not going to do it, figure out the expectation of this thing squared. So if the values of x go from k to n, k squared can be put in here. And then n choose k, p to the k, 1 minus p to the n minus k. And then you can simplify that, right? So it's a little more work. You kind of have to do it kind of 2 steps. So it's more work to do that. Figure out what that is, and then subtract n times p squared and simplify it. When you do that, it ends up being n times p times 1 minus p. That big mess simplifies into that as a variance. And standard deviation is the square root of that. So the standard deviation of a binomial random variable is the square root of the sample size times p times 1 minus p. So let's say we have 18 homes. And let's say that the probability that a particular home has internet cable in a certain area is 90%. And then you randomly take 18 homes to do an interview, gather some information on their TV viewing habits or something. How many do we expect to have internet cable? What's the expected number in this case? So the formula, right, the expected number, maybe I'll call it y instead of calling it x, which is the n times proportion. So there's 18 and 0.9, so that's 16, 16.2. 16.2 homes on average out of 18 randomly picked ones would have this. So 1.8 on average would not. Suppose instead you did a bigger survey, 1,800 homes. Right? Maybe the first 18 was kind of a pilot study, figuring out, can you actually talk to people? Can they actually answer the questions? You know, is it getting information that makes sense? Often large surveys do a pilot just to make sure the question wording is clear and it's computerized, that the interfaces and the web survey, that the flow and the skip pattern, right? You know, do you have internet cable? And they say no. Well, you're not going to ask them, do you like internet cable? It's like, well, I have it, so you know. So anyway, so there's a skip pattern where they don't ask certain questions. They have to make sure that works. Maybe they do 18. All right, 18 homes. If the probability is still 0.9, then the expected value of the number of homes, again, is 1,800 n times this. So it's 100 times what it was before. So it should be 1620 homes on average would have that. Right? The expected value of the number with the number that are without the cable, right, is going to be 1,800 minus that number, 1620. So 180 would be the expected number without the internet cable. So if you wanted to ask questions about both with and without, you'd expect to get 16, 20 one group and 180 the other, pretty imbalanced, just by random selection, right? Variance or standard deviation, right? So the variance of y here, 18 times 0.9 times 0.1, variance of 1.62. The standard deviation is the square root of that, which is not completely, 1.27, there it is. And that's back on the, in terms of counting homes. Right? An average of 16.2 and a standard deviation of 1.27. The variance up here of this one is 1,800 times 0.9 times 0.1, so it's 162. Right? So the standard deviation of this one, the square root of that, 162, is 12.7 homes. So these, right, the average and the standard deviation, particularly with these larger sample size, gives you some decent information about what type of values are possible. Right? We could look at some probability distributions, and next week we'll spend more time with computing. At least I want to, or some instructions will be given. We can make a little graph of this probability distribution, right? That in R, just getting started here. We'll just do some things here. Right? Is there are some commands for binomial random variables. And R binom is a function for generating random numbers, as if you were doing a binomial experiment. And under this help file, it tells a few things about the number of random numbers, the number of observations we want, the size, the number of trials. That's usually what we call N. So it gets told a little bit differently. And P is this probability. So if we do random binomial, and so we want just one observation, right? So with 50 pregnancies, 0.3033 as a probability. We do it once, we got 0 out of 50. Right? Do it again. Other times, we get different numbers. Right? You can tell it to generate more value. Say we do it 10 times, right? So this is out of 500 women, 10 sets of 50. We get different numbers. We do it like a lot of times, right? 50 sets of 50 women 1,000 times to make a table of those numbers. Sometimes we get 0, sometimes we get 1, sometimes we get 2, etc. The mean was 50 times 0.033, about 1.65. And so if you do an average, which is the mean function of these random numbers, it's pretty close to that. It's a little bit lower that time, a little higher that time, but we get about that number on an average. The other thing that this gives us, which is convenient, is this density, or the probability density function, right? The density at a certain size. So what's the probability that you get 0 out of 50? 0.33. 0.33, right? Gives us this probability, right? So the chance of none was 0.967 raised to the 50th, right? That was a chance that one didn't 50 times, right? And it's that probability. Or you could ask, what's the chance to get one woman, right? So that is 50. One woman is a multiple pregnancy, and 49 are not, right? And so you get that probability. So the densities are calculating the probabilities of specific ones. If you do something like 0 to 3, it's actually 3 numbers, or the 4 numbers in a row, like a sequence of numbers. So if you put that in there, 0 to 3, it's going to get the probabilities of 0, right, of these different numbers in there. You could add those up or subtract them if you wanted. The P binomial actually is the cumulative. Right? So the sum of these numbers is actually the same as the probability that you're at 3 or less. Oops. One extra. That you're less. So a lot of these binomial formulas are incorporated in this if you ever needed to do anything about planning or computing or check big calculations. Right? The homework will be a mix where you do some by hand, write out formulas, and then some computing. Right? One thing we can do with the computer, right, is we could make a plot. Right? So if it's out of 50 women, right, 0 to 50 are the possible values. Right? We could put the binomial densities at each of those values for the 50 women when the probability is 0, 3, 3. And these are all the binomial probabilities. Right? At 0, there's quite a lot of them. 0, 1, 2, 3, 4, etc. And then after a while, the chance that you would get, it's only 3% chance for each woman. The chance that you would get 10 out of 50 or 20 out of 50 is almost 0. It's not 0, but it's much less than 1%, or 1 in 1,000. And in fact, if you restrict this, say we only care about the first 10 values, right? We could do a plot. Here are the probabilities of 0, 1, 2, and you can see it a little bit more easily in there. We can do this with bigger numbers too, like the 1,800 houses. Right? We can look at the density of the binomial for 1,800. We're at 1,800, and what was the chance for each one? 90%? That's what that one looks like. Right? So that's the probability distribution. It's 0 for almost all the outcomes, right? Except in this narrow band where you have some chance of actually seeing things, right? Very likely to get, almost impossible to get 1,000 out of 1,800 when you expect the 1620. If we restrict this more to a relevant range, so 1620, so 1550, say, up to about 1750, doesn't necessarily, just for plotting like this, we don't have to be exactly symmetric. But that's what the probabilities look like. Right? Each individual probability is not so high because there's a lot of different possibilities. Right? But where is the average? But it's very symmetric, right? Once you get these large number of observations. Right? 1620 is here kind of in the middle. And one way to think about the mean and average is that you take the average plus or minus a couple standard deviations for something that's kind of bell-shaped like this. So you get about 95% of the area. About 95% of the probabilities add up. Between those values add up. So 95%, doing that with these numbers, you get down to a little bit less than 1,600 and a little, almost up to 1,645 or so. So about 95% of the values you're actually going to see when you do your survey are going to be in that range. You're unlikely to get 1,700. Can you guarantee me if you survey 1,800 and there's 90% that you'll get at least 100 that do not have internet cable to ask them questions? Can't really guarantee it, but it occurs with a really high probability. Probability that you're above 1,700, so you'd have less than that for that is trivial. Right? You feel very, very safe about it. Even though it could happen that everybody says I have internet cable, right? But it's a pretty safe bet that you're actually going to get at least 100. You're more likely to get actually 150 or 125 or 200, right? Be somewhere in here for the number with it, and so 1,800 minus that is the other one. But any questions about? There's one other way to get at mean and variance for this. So there's two little things, to kind of wrap this up. What value of P gives the largest variance? For a different random variable. So we have a binomial, random variable, small. With n and p. Variance, and say that's x. Sometimes I write x as a little twiddle there, and that symbol is pretty common in statistics textbooks or probability textbooks. So X is a random variable. Variable that has a binomial distribution. All right, binomial NP distribution. Some people say X is distributed as a binomial, means that it has those probabilities. It fits that model. Right? Kind of a shorthand. The variance, the expectation of X was n times P. So as you get more sample sizes, the mean's going up. As P gets bigger, closer to 1, it's going up. That's pretty clear. But what about the variance of X? N times P times 1 minus P. How's that affected by these things? Right? So as sample size gets bigger, that formula is going up, right? You get more trials, there's more variability in the range of different outcomes. Right? What about P? P can go between 0 and 1, right? What does the variance, or what does P times 1 minus P look like as a function? So you could write it as P minus P squared. So with the square there is a quadratic function. Is it concave or convex? Concave is tilted over like a cave, right? And convex is the other one, right?
Concave.
Concave, right? So it's going down, right? It's actually symmetric about 1/2. It actually looks something like this. At 1/2, the maximum value is actually 1/4 for the variance, right? And so it's actually increasing in the middle. Right? So you could use calculus to show that, for instance. So if you wanted to maximize P times 1 minus P, that function, over P, right? In calculus, how did you find the maximum of a function?
Find the critical point.
Find a critical point, right? So, which means take a derivative. Right? So take a derivative of this function with respect to P. Well, that's the derivative of P minus P squared with respect to P. So that's 1 minus 2 times P, and you set that equal to 0. Right? The maximum occurs where the slope at the top is 0, right? And the derivative is giving you the slope. So we're taking a derivative, right, and setting it equal to 0 so that it's flat on top. And then if you solve for P, this implies that P equals 1/2. This is where the maximum, or it's a critical point. Is it a maximum? We would take a second derivative. So we take a second derivative of this thing, P minus P squared. It's another derivative of this, and so it's -2, right? So that's less than 0, so P equals 1/2 has to be a maximum. So remember the second derivative being negative means that the slope, the kind of the tangent line slope, is changing from positive to negative, right? It's becoming smaller until it's tipping negative, right? So back over here, you have a positive slope, but as P moves along, this thing is turning negative. So the second derivative gives that decreasing change, and so that's concave. Right? So this is where the maximum happens at 1/2. So thinking about, this is, we're going to measure things. We're going to count numbers. So out of 50 women, we have 0 through, we have 0.03 as a proportion, 50 women. Other ones, some other things. What's the chance that, a woman is, goes to college? That's much closer to 50%. And in which of those two cases are you going to get more variance? What implication does a proportion near, say, 0 have for us? what are the outcomes you're actually going to see if the proportion is very small? What are those values K are likely? Well, 50 women, proportion 0.03, that's pretty small. Right? What are typical values we saw in those graphs?
1, 2, 3.
Yeah, 0, 1, 2, 3, small numbers, right? We didn't see things across the entire range, 0 to 50, very often, right? Because it was all concentrated there. That's low variance, right? If we looked at it the other way, what's the probability of a singleton birth? 0.697. Right? The variance is actually going to be the same, because p times 1 minus p, you can ask the number of singletons, the number of multiples, and do the same variance, right? If it's 0.697, what are your outcomes going to be out of 50 women? You're going to get 50, 49, 48 a lot of the time, right? Everything's going to be concentrated there, low variance, right? But if it's flip a coin, 50-50, right? Each woman, you either get yes or no, right? And so you get a lot more variability in that, right? If you actually look at that little probability distribution for that, right? We can see what happens, right? So 50 women, right? This was the plot when it was Control C, Control V, I can paste it back in. And that was the probability when it was 50. All the outcomes, 0, 1, 2, 3, are very concentrated. Right? However, if it's 0.5, right, we're over quite an extended range, right? 15 up to about 35, right? We get outcomes that are all over the place, right? That's bigger variance. Right? And so, kind of with calculus, you can graph that P1 minus P and see what affects it. Right? But anyway, so if you're measuring things and thinking about the outcomes, and P is really small or really big, it has low variance. But if it's in the middle, and it's equally likely to add 1 or add 0 each time, then it's more variance. Right? There's an alternative way, an alternative method for mean variance. So let's say we have n trials, each with probability p being success or failure, P1 minus P. Or yes, or whatever thing you're counting, failure, or no. And so X is the number of successes. Right, so X is binomial in trial. What happens if we keep track of each individual trial? What is the distribution for each individual trial? Each individual trial either gives us a 0 or a 1. Right? So really X can be just the sum of those things. Right? We add 1 if it's success in the first, add 1 if it's success in the second, and so on. Right? So if you do x1 plus x2 plus x3, we'll have to xn. Where xi is what is called a Bernoulli random variable. Put a little p there. So it takes a value of 1 or 0 with probability p and 1 minus p. So, and they're independent. They're all independent. These xi's are independent of one another. So if we can get the expectation and the variance of each individual trial, we add them up, and it turns out that we just add up the mean. Right? So what's the expectation of an individual one? We did this lecture ago or so. Each one of these has a value of 1 with probability p, or probability of 0 with 1 minus p. So each one just has an expectation of p. Its values could be 0 and 1. The proportional time is 1 is p. The proportional times is 0 is 1 minus p. And that's how it comes out. This is for each I. So the expectation of the binomial is the expectation of the sum of these xi's, I going from 1 to n. And the binomial, and the sum of the expectation of the sums is the same as the sum of the expectations. Expectation is a linear operator. It works out that way. Xi. And so each of these has a expectation of p. Well, there's n copies of it. There's p plus p plus p n times, which is n times p. So knowing that little fact that expectation is linear, and you can write that binomial as a sum, does that make the derivation a little bit nicer than dealing with all the summations and change? It's nice to be able to do both, but it's the same result. How about the variance of an individual? Well, there's a couple ways to do that. Here's this one thing where you take the expectation of the values squared, the variable squared, minus the expectation squared. So this is the expectation of the xi, the individual one squared. And this one over here was p, the mean, p squared. What's the expectation of xi squared? What are the values that xi squared can take on?
P squared.
So, but in terms of values, right, x can take 0 and 1. So x squared can take 0 and 1. Right? It's so 1 squared, and if x has probability p of getting that one, you get a p here. 0 squared times 1 minus p. And then we have this minus p squared. So we end up with p minus p squared, which we factor out to be as p times 1 minus p. So the variance of an individual Bernoulli, the 0, 1 variable, is just p times 1 minus p. Right? Now, if these variables are independent of one another, if the xi's are independent, then the variance of x, which is the variance of the sum, ends up being the sum of the variances. There's no covariance terms between them. They don't affect each other. So it ends up just being sum of the variances. That's another fact about expectation and independent variables. So each one of these is p times 1 minus p. And there's n of them. So it's just n times p times 1 minus p. So knowing this extra fact about expectation simplifies finding the mean and variance quite a bit over doing all the manipulation of the summation signs before. But any questions about? Yes?
I'm sorry, what is after the summation n? What does it say after that?
This one equals n times p times 1 minus p.
No, the symbol right after the summation sign?
P is supposed
Oh,
to be a little p.
sorry, thank you.
No. So that's just another way of getting at the mean and variance, right? So we've talked about this binomial random variable examples, computing probabilities in its applied settings. We did a little bit of theory about the average, variance, a little bit of derivation. Most of the work we'll do on the assignments and things will be applied. But like the story proofs, there'll be a little bit of connections, because that's kind of a little bit deeper, a little bit more math to do that, to see kind of inside how things work a little bit behind the scenes instead of just numerical applications. The plan for no lecture on Thursday. It's a official college break. Come back, we'll look at a little bit more chapter 4. There's other special models where we can figure out probabilities and get equations and means, and do a little bit of that for other ones. Like some applied, a little bit of theory, to a little bit of thinking about why does it make sense. Right? Like why, if p is 0.5, you get the most variance. What does it turn into your measurements? Right? So connecting the actual things you measure, like the statistics that you might get in the actual survey, the answers, they are influenced by these probability distributions. And so understanding some of the connection gives give some insight. On the website, under, no, I know it's not there, so, but I will post, I have a little handout that, is I wouldn't say easy, but it goes through some numerical examples and some questions about is a certain scenario binomial or not, and there's some solutions to it, so I'll post that. It'll just be something to read through as to check understanding about computing some of the factorials, or the combinations, and answering a few of the questions. So that'll be a study material posted with this today's lecture. Okay? I'll collect the homework 2, next, this is homework 3 coming in, right? And then another one will get posted.
When will our homework start incorporating R stuff?
Soon.
But not for next week.
We'll see how much time, and I'm thinking about when we do, because we don't have class on Thursday. Would we get that have it on Tuesday or Thursday? Later than I will, I can't think. It'll be gradual. Great, thank you. Yep. Oh, yes. I have a meeting until 1:30. So if I'm not there, you could just slide it into the door.
You mean
Yeah, after 1:30, I'll be around. So.
or you will be around after 1:30. So what if I can get it
Thank you.
before 12, so it will be.
Oh, yes, I'll be in
Okay.
Yep.
Sorry I was late. I had a call with my internship for the summer and it ran a little, I tried to schedule it before and I thought they were scheduling in Eastern Standard
Thanks.
Time, but they're in Iowa.
Oh.
So they were central, so I
You're going to Iowa for the summer?
Yes, I'm going to work at Principal over the summer.
Good.
So sorry I was late. I'm
Are
not.
you in Des Moines or in Iowa City?
Des Moines.
Des Moines.
Yep, I'm in the U.S. Insurance Group.
Okay.
Have a good day, Professor.
Yep, I was in Iowa for 6 years.
Oh, cool.
I grew up in Nebraska, but then I was at Iowa State University for 6 years in Ames.
Mhm.
Des Moines has some neat stuff that happens over the summer.
Pretty much the state fair is what I've heard.
The state fair, but they have some festivals.
I heard about the bike ride too.
Oh,
there's a
rag
bike-
ride, yeah, across the.
So I'm excited.
Good.
Not bad.